Let's talk about the second derivative test. Suppose we have that the derivative at the point C is equal to 0. As we know, this means that C is a critical number or a critical value or a critical point. And let's say that the second derivative is continuous. It's a continuous function over an interval I that contains this point C. Okay, so I'm going to explain the second derivative test by drawing a picture for you. We're going to have our line that looks like this. That's kind of representing our interval. And here's our point C over here. And what we're really trying to do is we're really trying to classify this critical point. And let's say that at that critical point, your second derivative is positive. In other words, the situation is concave up. And your second derivative here, evaluated at C, is greater than 0. That your function is going to have a minimum at C, at x equal to C, let's say. Okay. On the other hand, if when you look at your second derivative and your second derivative is negative, that means the situation is concave down, right? This means that your second derivative evaluated at C is negative. That implies that you're going to have a maximum at x equal to C. So what's the third case? The third case, let's draw another little number line. Here's C. In this case, when you look at the second derivative at C, let's say the second derivative is 0. So f double prime evaluated at C is equal to 0. What this means is that the test is inconclusive. In other words, it's neither concave up nor concave down. Okay, so one possibility, I'll just make a comment here. We may have an inflection point at C in this third case. You won't really know until you look to the left of C and the concavity changes when you move to the right of C. That's what the definition of an inflection point means. So, maybe it goes from concave up to concave down, or from concave down to concave up. If either of those situations happen, then C would be an inflection point. Why don't we take a look at an example together? Let's take a look at example 4. So when I look at this, what's the first thing that I need to do? The first thing I need to do is I need to find the critical values. So let's find the critical values. Okay. So in order to do that, I need to calculate the first derivative. So when I calculate the first derivative, I'm going to get 5x to the fourth minus 15x squared. When I look at this first derivative tells me that I have a common factor of 5x squared, so I could factor that out. And when you look and see what remains, you're going to get x squared minus 3. Okay? Then when I look at this second term over here, I can think of this as a difference of two squares. So when I think of that as a difference of two squares, I can factor that as follows. That's going to be 5x squared. That's the common factor. I can think of this as x plus rad 3, and this is going to be x minus rad 3. So that's viewing this as a difference of two squares. Difference of two squares. All right. So setting that derivative equal to 0, this tells me that my critical values are going to be x equal to 0. That's for this first term, x squared. It's going to be negative rad 3. That's going to correspond to the 0 of the second factor, and x equal to rad 3. And that's corresponding to the 0 of the third factor. All right. So then the next thing I need to do is I need to calculate the second derivative, because the second derivative is what gives me information about concavity. So the second derivative of f, that's just going to give me 20x cubed minus 30x. So in this particular case, I could factor it if I wanted to. I don't really need to factor it because really I'm going to use this second derivative to classify my critical values. So what I'm going to do is I'm going to plug the critical points into the second derivative. I really should just call that f double prime, I guess, to classify. Okay. Then. So let's do that. I'm going to calculate what f double prime of 0 is going to be. When I calculate that, that's just going to give me 0. When I calculate f double prime of negative rad 3, that's going to give me 20 times negative rad 3 squared minus 30 times negative rad 3. When you evaluate this, this is going to give you a negative number. So that means that, negative things make me sad, and we're evaluating this at negative rad 3. So this means that we have a maximum at x equal to negative rad 3. So that's our first meaningful extrema. Okay, and I'm going to plug in the second derivative. Into the second derivative, I'm going to plug in the rad 3. This is going to give me 20 times rad 3 squared minus 30 times rad 3, like this. In this case, this is going to give me a positive number. So this tells me that, positive things make me happy. So when I'm at rad 3, it's concave up. This tells me that I have a minimum at x equal to positive rad 3. So let me highlight that guy. Okay, so just to recap, my first critical point was 0. That's the inconclusive case, so that's not an extrema. At negative 3, I had a negative second derivative, so that means that it was concave down, which corresponds to a maximum. And at positive rad 3, that's the second derivative is positive. That means it's concave up, which means you have a minimum at rad 3. All right, everyone. We'll work on some examples in class together. Take care.